Hey everyone, my name is Mohammed Haris and I am joined along with Aaron Ramirez and Thai. Today we are very excited to present our work on detection and prevention of vehicle insurance claim fraud using machine learning fundamentals. Our project objective is to leverage advanced data algorithms to accurately detect fraudulent claims, ultimately protecting insurance companies from financial losses and ensuring fair premium rates for honest customers. So let's move on to the next slide. Understanding the problem. Insurance fraud is a pervasive issue with far-reaching impacts. It costs companies millions of dollars each year, directly affecting their profitability and leading to higher premium rates for honest policyholders. Detecting fraudulent claims is crucial for minimizing these financial losses and maintaining customer trust. To illustrate the scale of this problem, consider that in 2022, the insurance industry in the US generated over 276 billion in revenue. However, foreign claims affected many industries, including tourism, dining, and accounted for almost 23 billion. By addressing this problem, we can help insurance companies save significant amounts of money and ensure a fairer system for all customers. Executive summary of our project. So our project focuses on developing a reliable, predictive model to identify fraudulent insurance claims using historical data. So our problem statement is, how can vehicle and policy data be leveraged to accurately detect and prevent fraudulent insurance claims? Our primary goal is to create a model that accurately distinguishes between legitimate and fraudulent claims. The benefits of achieving this goal are substantial. Reduce financial losses. By detecting fraud early, we can prevent significant financial losses for insurance companies. The second is enhance operational efficiency. Our reliable model can basically streamline the claims process, allowing companies to focus on legitimate claims and improve overall efficiency. And the most important is boosting customer trust. By ensuring that only legitimate claims are approved, we can enhance the trust customers have their in insurance providers. This project aims to accurately detect and prevent fraudulent insurance claims using historical data, thus providing a more robust solution for this industry. Let's move on to the dataset analysis. To build our predictive model, we utilize a comprehensive dataset from Kaggle, which includes 33 variables, both categorical and numerical. Our dataset analysis involves several critical steps to ensure the quality and reliability of our data. Starting with understanding the data. We begin by thoroughly examining the dataset to understand its structure and content. This step is very crucial for identifying any potential issues that could impact the performance of our machine learning models. We specifically look for missing values as they can significantly affect the accuracy of our predictions. The next in line is data cleaning. Ensuring data integrity and suitability for model training is very essential. We conducted an in-depth analysis to comprehend the data's structure types, and initial statistics. This process involved identifying and handling outliers, addressing missing values, and ensuring that the data was accurate and consistent. The last is encoding and scaling. To prepare our data for machine learning algorithms, we converted our categorical variables into numerical formats using techniques such as one-hot coding. Additionally, we standardized numerical features to ensure consistency and improve the model's performance. By following these steps, we ensure that our data set is clean, reliable, and ready for accurate predictions. This rigorous data preparation is critical for the success of our machine learning models. So we believe that our approach, grounded in thorough data analysis and advanced machine learning techniques, will provide a more robust solution to this pressing issue. So thank you for your attention. I will now hand it over to Thai, who will walk you to the exploratory data analysis and feature engineering. Thank you and have a wonderful day. Bye.
Thank you so much, Mohammed. Let's start our exploratory data analysis by examining the distribution of fraudulent claims in our dataset. As depicted in the pie chart, a substantial majority, 94% of the claims are legitimate, while only 6% are identified as fraudulent. This significant class imbalance presents a considerable challenge for accurately detecting fraud. The rarity of fraudulent claims necessitates the use of highly robust and precise models to ensure effective identification. Detecting these rare fraudulent claims among a large volume of legitimate ones is critical for minimizing financial losses and maintaining the integrity of the insurance system. Our analysis and model development efforts are thus focused on addressing this imbalance to enhance fraud detection accuracy. Moving on to our feature analysis, we begin with the histogram of deductible amounts, which show high concentration around 400, suggesting that most claims have deductibles amount of 400. Next, we examine the age distribution of claimants, which reveal the majority of claims come from individuals aged 20 to 50, with a notable peak around 30 to 35 years old. When we look at the distribution of deductibles by fraud status, we observe only slight differences between fraudulent and non-fraudulent claims. However, the age distribution by fraud status provides more insight, showing a higher incidence of fraud among individuals aged 25 to 35. This information is crucial for guiding our feature engineering and model tuning efforts. By understanding the impacts of these features on fraud, we can make more informed decisions about which features to include in our models and how to pre-process them to enhance detection accuracy. Visualizing these distributions help us comprehend the underlying pattern and informs our approach to building robust predictive models. In our feature engineering process, we begin by extracting key features from our dataset based on insights gained during exploratory data analysis. These features were selected due to their potential impacts on detecting fraudulent claims. To prepare the data for modeling, we applied one-hot encoding to categorical variables, converting them into formats suitable for machine learning algorithms. For numerical features, we used scaling to ensure they had consistent range, which is crucial for many machine learning models. Additionally, we addressed missing values and handled data imbalances using techniques like SMOTE to balance the classes. Ensuring data integrity through thorough pre-processing steps was a priority. This included verifying the correctness of data types and managing any anomalies. By engineering these features and applying robust pre-processing techniques, we aim to enhance our model's performance, making it more effective at identifying fraudulent claims. This comprehensive approach to feature engineering and data preparation is critical for building reliable and accurate predictive models. In our feature selection process, we identified 10 key features that were crucial for detecting fraudulent claims. These features were selected based on the results of chi-square and t-tests as well as domain knowledge. The selected features included age of vehicle, age groups 18 through 50, past number of claims, vehicle price, vehicle category, base policy, fault, deductible, policy type, and sex. We visualized the distribution of these features to understand their impacts on fraud detection better. For instance, we noticed that a certain age group and vehicle categories had stronger associations with fraudulent claims. These insights guided our feature selections, ensuring that we included features with the most significant influence on fraud detection. By focusing on these relevant features, we optimize our model's input, making it more effective in identifying fraudulent claims. This careful selection of process ensures that our models are not only accurate but also efficient in processing and analyzing the data. The combination of statistical tests and domain knowledge provides a robust foundation for selecting the most impactful features for our model.
Thank you, Ty. In our project, we explored several machine learning models to detect fraudulent vehicle insurance claims. The models we trained included isolation forest, gradient boosting, decision tree, XGBoost, random forest, k-nearest neighbor, logistic regression, and cat boost. Each of these models bring a different approach to understanding the nuance of our dataset. We evaluated these models using key metrics such as accuracy, precision, recall, and F1 score. These metrics provided a comprehensive view of each model, allowing us to identify which model best balances the need for identifying fraudulent claims without raising too many false alarms. After training our models, we compared their performance based on the evaluation of metrics. The graphs here provide a visual comparison of each model's accuracy, precision, recall, and F1 score. Overall, you could kind of see they're very similar to each other, minus isolation forest, but we'll get more deep diving into it as we talk about the numbers itself. Starting with accuracy, CatBoost achieved the highest score of 86%, closely followed by Random Forest and SGBoost. Precision, which is the measure of accuracy and positive predictions, showed similar results to CatBoost, leading at 80%. Recall, an indicator of how well the model identifies actual positives, saw Cat Boost once again at the top with a remarkable score of 94.6%. Finally, the F1 score, which is the balance of precision and recall, also highlights Cat Boost as leader, which was at 87%. To go back onto isolation forest, while this method is useful for anomaly detection, it showed significantly worse performance across all metrics during this evaluation. This indicates it is not suitable for our fraud detection needs. Given these results, we selected CatBoost as our primary model for detecting vehicle insurance fraud due to its superior performance across all the key metrics. In conclusion, our comprehensive analysis of various AI models for detecting fraudulent vehicle insurance claims highlighted the CatBoost model as the top performer across all key metrics. This model's ability to handle category data efficiently and manage class imbalance effectively makes it particularly well suited for complexity of fraud detection. By leveraging the strength of CatBoost as a primary model and using random forest and XGBoost to complement it, we can achieve a comprehensive and reliable fraud detection system. This multi-model approach ensures higher accuracy and reliability in identifying fraudulent claims, providing a solid foundation for more efficient and trustworthy claim process. Incorporating multiple models allows us to cross-verify claims flagged as potentially fraudulent, reducing false positives and improving the overall trustworthiness of the fraud detection system. This layer approach not only enhances the precision of detection, but also provides valuable insight into the different dimensions of fraud, enabling continuous improvement and adaptation to evolving fraud tactics. Finally, going into implementation and recommendations, we recommend deploying the CatBoost model as the primary tool for detecting fraudulent vehicle insurance claims due to superior performance. To ensure robustness, random forest and XGBoost can be used as supplementary models. Continuous monitoring and periodic retraining of these models are essential to adapt to evolve fraud patterns and maintain their effectiveness. Additionally, integrating these models with claims processing system will automate fraud detection to enhancing both efficiency and accuracy in handling claims. I also want to touch on the point that before full implementation happens, this needs to be tested on other data sets, and I would like it to be tested on other countries' data sets as well, due to their policies can be a little different than the US's. The goal is to try to make a model that will suit best for the insurance industry overall. So following these steps afterwards will help continue to get us to those to the path that we need. Next, for the societal impact. The societal impacts of implementing advanced AI models for fraud detection are significant. Firstly, it provides financial protection by reducing loss for insurance companies, which will result in lower premiums for customers. This enhances the affordability of insurance. Secondly, the fair and transparent process of claims can build customers' trust, leading to higher satisfaction and loyalty. Lastly, by setting a benchmark for fraud detection, we can encourage other companies within the industry to adopt similar technologies, driving overall improvement in the insurance sector and standards and practices, excuse me. Overall, this concludes our presentation. Thank you very much. All right, now to go over the screencast of the code overall. As you can tell, this is going to be the prevention and detection of vehicle insurance claim frauds. As you look, we started with data integrity, going into encoding and scaling, looking into EDA, feature selection, feature engineering, model evaluation, deployment, and discussion and conclusion. So first, obviously, we're just importing everything in. Afterwards, we imported the file in itself and then started looking at the data overall. We ran through descriptions just to get a little bit more idea of what the data is. Next, we started cleaning the data. We checked if there was anything missing. There wasn't anything missing, which was really good. After that, we started looking into the types. The types that is needed. This is key because if we need to start hot encoding, which I'll get more into later, then we can, or if we need to convert them to make it easier to flow for us, essentially. So we actually did do some converting. We converted fraud found P into bool, and then we converted year into object as well. We also tried to make sure we categorize by numericals and categoricals, and then we displayed it. And then finally, we went into EDA. So exploratory data analysis, the first thing we did was just do an overall pie chart to see
if it's like a 50-50 split, if there's fraud or not, as is shown, like in real life, it is not. It is very minor. It's only 6% that is true fraud. Other than that, it's not fraud at all, which is shows that we're gonna have to use other techniques to impact this data. Going into the numerical feature analysis, so within the first couple of charts, the huge things that we found was age and the deductible could potentially be used to try to understand fraudulent activity. We saw just basically how they're layered and the different ways it looks overall. Going into the next one for the target-based feature distribution, again, age kind of showed the biggest hurdle with it, which it reinforces why we need to keep age as a factor. And I'll get more into why age matters in a bit. Next, we went into box plots for outliers. We compared the distribution and we found there was a couple of outliers with age and deductible, so we ended up removing them overall. Next, we went into the chi-square and the t-test. For the chi-square, we found that these could potentially be used overall. Sorry, when I say these, I meant the bullet points listed out can be used overall to be able to detect fraud. And then for the t-test, the ones we found as well were age, policy number, and deductible. Going into categorical feature analysis itself, biggest thing is just looking at the distribution of everything. I apologize for it to be a little bit messy, but there was just some formatting issues with the code. After looking at that, we found that fault, policy, vehicle categories, base policy, the price, claims, the make, the gender, age of vehicle, and address change could potentially, but not all of them fully. Finally, we go into the SNS, which is the pair plot. This is showing overall that this problem itself is more complex than just, oh, like, these one or two variables, you can figure it out from there. No, it shows, this overall shows that it is a very complex problem with just how the data itself is kind of all scattered everywhere and seeing different types of plots itself. Finally, we went into correlation matrix. There really wasn't too much found. We found a little bit with like week of month and week of month claim, but nothing too crazy. And then finally, we go into feature engineering. So from the EDA itself, as well as reading into some of the domain knowledge and the history of what was happening within insurance fraud, we came up with these categories overall. So age of vehicle, age groups 18 through 50, past number of claims, vehicle price, the vehicle category, base policy, fault, deductible policy type, base policy, and sex. This was the a combination of both EDA as well as the domain knowledge. So next we go into feature extraction to be able to pull them out. We one hot encoded the categorical categories. We standardized in numerical so that way no outliers can hugely affect it. We pulled out the target variable and we also applied smelt. This is because there was only 6% that was considered fraud. If we're having such a small amount, it wouldn't have helped us at all. Next, we split the data and then we went into models. So the first one was isolation, and then we messed with tuning, and then that's how we kind of got our results as well, and then so on and so on. Now we have gradient boosting. Oh, sorry. And then this last line, I apologize, is basically putting it into a list or a dictionary just to make it easy for us to show at the very end. Next, we went to gradient boosting. Here's the results before, and then the results after with 8544. And then adding it. Next is the decision tree classify with 85%, and then the upgrade 85% about the same. XG boost 84%, and then tuning it 85.7%, so a little bit higher. Random forest 85.5%, and then with tuning 85.7%. With KNN 82.2% and 84.4%. Logistic regression 79%, and then when you tune it, the best one I believe was about 79.4%. And then finally, model with cap boost 85.7%, and then at the very end 85.8%. Once we go into results and conclusions, this is where we start analyzing them. This is how we saw cap boost barely narrowed it out from the rest of them. And yeah, that's pretty much all our code. We have our results of how it all looks and the conclusion. We talked a little bit about that in the PowerPoint. Thank you very much.